you doing?
Well, I've been working on my new hair growth serum. It's been working incredibly well. And unfortunately, with all the social distancing, I'm not going to be able to get this haircut for a while. Did you need something?
I was wondering if you could explain KSP.
No problems. All right, first, we need to talk about all these different Ks that you've been seeing. Now, you're all familiar with this K with a C. We used to use those back when we first learned about equilibrium. And we also saw Ks with a P. Now, these Ks stand for the exact same thing. Each of these Ks represents an equilibrium constant. And then these letters just tell you what kind it is. In this case, it was concentration. And the P, well, that stood for pressures. So just knowing that you're dealing with equilibrium, just different kinds of variables. So now all of a sudden, you're going to start using a new K. And this K has a little s and a P next to it. Now the S and the P represents the term solubility product. So again, it's another form of equilibrium, only this time it's going to deal with the solubility of something. And just keep in mind as we move forward, you're going to see Kas and Kbs also later on next week. So each K is an equilibrium constant. The subscripts just tell you what kind it's dealing with. So now I need to explain to you how you actually write a KSP expression. So I'm going to do this for the two following salts that you see on the screen. So just remember this, that when a solid is going to dissolve, it's going to split into its subsequent ions into the solution. The way you write a KSP expression is you actually do it just like an equilibrium expression. Although, remember, we do not write the solids into our expressions. So this one would actually look like this. Ag concentration times the bromate ion concentration. Now the difference in the second compound, it happens to have two. This is a solid. Oops, I made a mistake. It happens to have 2 plus 2 hydroxide ions. So this is going to change the expression just a little bit, but given that we've written these before, it's not that complicated. You're going to have the cadmium ion times the hydroxide ions. However, this is going to be squared because the coefficient must become the exponent. Now let's calculate KSP from solubility. Here's an example question. The solubility of silver bromate in water is 0.0072 grams per liter. Calculate KSP. Well, for starters, we can't work with grams. We work with molarities. So first thing we have to do is convert this to molarities by dividing by the molar mass. But luckily for you, I happen to have it memorized. For every 235.8 grams, you will get 1 mole of silver bromate. This gives you a molarity of 3.05 times 10 to the negative 5th molarity. Now, keep in mind, if we look at the actual dissociation of this solid, it gives us a silver ion, bromate ion. So the KSP expression is going to be the silver molarity times the bromate molarity. And as you can tell by the expression, for every mole of solid that dissolves, you get the same number of moles of silver and the same number of moles of bromate. So therefore, the KSP is simply going to be 3.05 times 10 to the negative 5 squared, which is equivalent to 9.3 times 10 to the negative 10th answer. And remember, no units to equilibrium expressions. So now let's try a different problem that's just a little bit different but much the same. The solubility of cadmium hydroxide in water is 1.14 times 10 to the negative 5 moles per liter at 25 degrees Celsius. What is KSP? So the thing you have to remember in this case is when you write equilibrium expressions, how the coefficients play in. So when cadmium hydroxide dissolves, you're going to end up with this expression. What this means to you is the KSP then is going to be equal to the cadmium concentration times the hydroxide concentration squared. It's a very important distinction between this one and the previous example. Now, something else that you need to realize is if I was to create an ice chart for this problem, you have to understand that initially there won't be anything dissolved, but as the cadmium is created, it's created at plus X, and the hydroxide is created at plus 2X because of its coefficient. So when it's said and done, then the equilibrium values for cadmium are going to be X, and the equilibrium value for hydroxide is going to be 2X. And so when you plug those values in, you realize that you're going to end up with X times 2x squared. Now, the question actually gives you the value of x because this is the solubility of the salt. Given that, that means that that's the amount of moles that actually that will dissolve. So anyways, when you plug in this value, you end up with this. 1.14 times 10 to the negative 5th times 2 times 1.14 times 10 to the negative 5th squared. And if you put all that into your calculator, you should easily calculate it to be 5.9 times 10 to the negative 15th. And again, no units. Now let's take a look at what we call the common ion effect. In this question, we are actually going to dissolve something into a solution that already has an ion that's contained in the original substance. So if you take a look at this, you notice there's a sulfate ion in the sodium sulfate, and there's also a sulfate ion in the strontium sulfate. So what this means is there's already some sulfate there. This is going to create an issue that we call the common ion effect. And so the common ion effect will affect the way you approach these problems, but it's very, very simple. Let me explain. If I was to take a look at the way strontium sulfate dissolves, it looks like this. And if I was to create an ice chart, I could actually see that when I put these in, yes, I will start with no strontiums, but it looks like I'm going to actually have already 0.10 molarity of the sulfates. They're there from the previous salt. Because this is a soluble salt, all of it is here. So, because of this, as this increases by an x and this increases by an x, that my final equilibrium values are going to be x and then 0.10 plus x. And I have to take that into account because my KSP expression for this salt is going to be the concentration of the strontiums times the concentration of the sulfates. So this works out to be x times 0.10 plus x. So I could set this equal to the KSP written in the question, and I can solve for x, which will then equal the solubility. Now, before you get real nervous and think, oh no, I have a quadratic formula set up, if you remember, you can ignore this x right here when the value of k times 100 is still less than your original molarity. So in this case, something to the -7th times 100 is going to be in a value of the -5th. That's nothing compared to 0.1, so therefore I can ignore it. So this allows me to just plug the numbers in, and just to save you the time, the correct answer when you're completely done should come out to be 3.2 times 10 to the -6 molarity. So that's how you work with KSPs. What do you think?
That's amazing.
I know.
Hey Dad, what's with this new shampoo?
Oh no, Matthew, you shouldn't have used that.